Hi everyone, we are Team DivMARL. My name is Mansoor. I'm a master's student at the University of Alberta, and I had a great pleasure of working with Jihu Yang, research engineer at Zoya Bang Education Technology, and Daniel May, PhD student at the University of Alberta. Here's a brief overview of our algorithm. We look at the observation from environment and compare it with the training dataset. If they match exactly, we simply use our DivMARL agent that was overfitted to training dataset. Otherwise, we can be sure that we are dealing with an unseen building from validation or test. So we compute actions using two different methods. One is rule-based controller and another is DivMARL agent. Then we find the average of these two actions and use it for unseen buildings. In this presentation, I would like to explain our rule-based controller and DivMARL agent that was used both for train and validation. Our rule-based controller is a decision tree with two levels, and it uses predictors for fixed load and solar generation in the next hour. First, we make predictions for the non-shiftable load and solar generation, and we define delta to be equal to their difference. In case when delta is positive, meaning load exceeds solar, we decide to discharge. We discharge by the amount of delta, but we place a cap on the maximum discharge rate. If next hour is crucial, then the cap is 40% of the battery capacity. Otherwise, it is only 10%. In case when delta is negative, meaning solar exceeds the load, we decide to charge. In the case when next hour is crucial, we actually completely prohibit charging because the prediction of delta might be inaccurate, and we notice that during crucial hours, solar generation is rarely above load. So probably negative delta is a wrong prediction, and the mistakes cost a lot during these hours. So no charging here. In normal hours, however, we allow charging by the full magnitude of the delta. For predicting fixed load for the next hour, we use an XGBoost regressor. And as features, we supplied SynCost transformed month and hour of day, one hot transformed day of the week, as well as fixed load for the past 24 hours. Importantly, we maintained fixed load history separately for each hour of the day, and as a feature, we included past 16 days average for the next hour. To arrive at this model and features, we conducted cross-validations, and here you can see prediction accuracies for 5 validation phases. And we were able to achieve R2 score of 54%. Predicting solar generation was much simpler. The model was linear regressor, and as features we used solar generation for the past 2 hours and average solar generation across train buildings for the past 2 hours and for the next hour. These are validation accuracies, and the average R2 score was very high. Next, I will describe our DivMARL agent, for which we had one decentralized soft actor critic per building, and it was shared among all buildings. I will only list the most important observations that we added. For individual features, we added one hot encodings of the building ID, which runs from 1 to 5. And from the previous time step, we fetched some important features like carbon intensity, fixed load, and solar generation. Also, we added past 16 days averages for fixed load and solar generation for the next hour, for the hour after the next, for the 6th hour into future, and for the 12th hour into future. We were hoping that these averages would capture the load patterns of each building and help predict fixed load and solar generation. Then, to do well on cooperative objectives, we used averages of all buildings for some features like fixed load, solar generation, and state of charge. We also added past 16 days averages here too, and they are exactly the same as individual features case, but averaged across all buildings. During training, we performed normalization of observations and rewards to zero mean and unit standard deviation. For that, we ran the simulation for 5 years with random action sampling, and we found mean and standard deviation values of collected observations and rewards. We also set the episode length to 1 week. During evaluation and testing, for each unseen building, an agent would compute an action 5 times because the building IDs that would normally go into the observation, they correspond to training buildings, but during evaluation and testing, we don't encounter them. So, varying building ID from 1 through 5, we get an action 5 times, and each action comes with its standard deviation, measuring the confidence in this action. And each action gets a weight inversely proportional to that standard deviation, and the final DivMARL agent's action becomes 1 over STD weighted average of the 5 actions. We found it to work better than simple averaging of the actions. As for the model, we used the standard soft critic architecture, but it was also augmented with autoencoder. The encoder takes the observation and converts it into an efficient latent representation, which is passed to separate critic and policy networks. Decoder tries to reconstruct the original observation from the latent representation. And we found that this autoencoder improves the speed of convergence by a lot. The last crucial piece of our agent is the custom reward function. The first step was to compute costs. The price cost is the positive net electricity consumption multiplied by electricity pricing, and carbon cost is the same but multiplied by carbon intensity. The ramping cost is the absolute value of the difference between district net load at the current time step minus at the previous time step. For the load factor, we consider the window of size 730, which corresponds to roughly 1 month. And we found the average to peak ratio over that window for the district net load. And we subtracted that ratio from 1. Then, for example, to calculate the price reward, we computed the price cost for the no battery agent and subtracted price cost for our agent. We also divided this difference by the total price cost of the no battery agent over the whole year of all buildings. The numerator gives the cost savings, and the denominator ensures that the scales of different reward components are equal. So the carbon reward takes the same shape, and ramping and load factor rewards are very similar, except that they are also divided by 1 over n. The reason is that each building is responsible for 1 over n of the cost savings. Finally, we do a weighted average of these rewards, and the weights assigned to each component are exactly the same as in the competition objective function. To sum up, we described our algorithm that combined role-based controller with DivMARL agent. Our methodology allowed us to achieve 30% reduction in overall costs for training dataset and almost 20% reduction for the validation dataset. That is everything for our team, and if you have any questions or want to discuss something, you are welcome to reach us using any of the email addresses shown. Thanks a lot for your attention.